Hi, I'm Anthony Suresh Arpudaraj, and today I'm going to do a video presentation on the element distinctness problem and its lower bound proof. And this is part of the course at UCF, which is COT5405, which is handled by Professor Dr. Shankar Pankaj. Let's take the question at hand. The problem at hand says that you have a sequence of numbers x to x, where you have n number of elements x1, x2, x3 goes on to xn, and you would be finding out if all the numbers are distinct. Then you would say yes. If one or two, if two numbers are non-distinct, then you would say no. Like for example, let's take an array with 5 numbers, for example, and let's just take for example the numbers are 2, 1, 4, 7, and 9. Okay. So what does this say? All the 5 numbers are distinct. So we are going to print an yes. If for example this 4 is being replaced by a 1 in the array, then you have 1 and 1 together, so you will be printing it as a no. Okay, and basically we are going to try to prove that the lower bound of this problem will eventually be omega n log n. So the most trivial way to solve this problem is we will be sorting these numbers. We'll make these numbers look like 1, 1, 2, 7 and 9, and then we'll check any two numbers which are close to each other because we've sorted obviously, and if it's equal then print no. If none of them are equal then we'll print yes, and for this we will be seeing that that is the most trivial solution. We'll be trying to understand the trivial solution also and try to make a better solution out of this. For this we would employ a lot of steps. We'll be looking at n-dimensional geometry to prove this proof, non-trivial proof, and then a proof of contradiction, where you are going to solve something, you want to prove it is true, so you will take a false narrative and try to prove it's false so that the true is automatically proved. We'll come to this in the next slides. Let's first check at a decision tree model to solve our case at hand. When we think of a trivial way to solve this element distinctness problem, what we can do is we can sort the numbers at hand, the elements at hand, and once they are sorted, we could check two numbers. We can compare two adjacent numbers, and if they are equal, then they are not distinct. If they are not equal and all the numbers are distinct, then so this we can solve it using a decision tree model like we have seen before also. So here, when you see here, in this case, let's take for example x is equal to 1, 2, 3, and this 1, 2, 3 could be of any size. Let's take this as xi and xj and xk. Now here what we do is we plug in the first two numbers into this root. This is a root, and from root what happens is we start comparing on the edges, and then based on that we arrive at a sorted output. The sorted output can be of L leaf nodes, and this leaf nodes is usually the number of n factorial of the number of elements. Here we have 6 because we have 3 numbers in this case, which is n factorial, which is 6, and therefore we also know that the tree height is our lower bound for sorting, which is omega n factorial, which is omega n log n. But here the answer is n log n factorial possibilities, like because every leaf will give you a different sorted output or a different iteration. But our requirement here in this question is just a yes or a no. So therefore you get only 2 possibilities, but this decision tree model that we have currently gives us a lot more possibilities than your yes and no. And when we take yes and no into consideration, we get only 2 leaves, correct? 2 leaves, and that is becomes n log n, which is log 2, which is 1, which is of no use. So therefore we need to come up with a better approach to solve this element distinctness problem that we have at hand. Now we are going to find out P of n for the lower bound proof for this element distinctness problem is omega n log n from decision trees. Now let's what we are going to try to prove is that a region R is there which has all the instances of the problem reaching a leaf node L at the end of the execution contained in a region R. So there is a region, let's take it as a dimensional space. Okay, let's take it as an n-dimensional space. For example, here we have n-dimensional space which says x1 and x2 are different elements from the array x, and now if we see x1 is equal to x2 is the straight line, and that is a no possibility, and other than that are all yes possibilities, which will prove that the elements x1 and x2 are distinct, therefore the x list is distinct. And we are trying to prove this entire region is one space, and subsequently when you try reducing it on a decision tree, when different numbers are added as different geometrical entities, this region will keep shrinking, but your point or all the numbers x1 to xn will stay in the same region. Let's take an example of a 4-dimensional space. This is just for our understanding from where we are getting at in a tree model. What we are trying to prove is, for example, let me show you. So what we are trying to show here is the entire leaf, any iteration, this is one iteration, this is one iteration, this is another iteration, all these iterations will end at L, and this will be part of region, correct? And so therefore when you take a 4-dimensional space also, what happens is, let's take this one as x1, this as x2, and now we have one as x3. If our point is less than x3, then your point is somewhere here, and that will be a region, half of this region. So if you see here, so this will be half of this cube which will contain. Subsequently you keep breaking down the region, it keeps shrinking. So what we are saying is, when there are 2 points to reach a leaf node L, then all the points are in a straight line inside a region and does not go outside a region. And our overall proof is, we need to find, therefore what we are trying to prove is, let's take x, okay, and this x will have x1, x2, x3, so on till xn. And now we have another one called y. We think we decide that x and y belong to region R of L. Both reach L leaf node. Okay, and so y will be y of n, y of 2, and y of n, and this y is a permutation of x. For example, x will, let's take x as 1, 4, 3, y will be 3, 4, 1. So they are the same numbers but a different permutation. Now let us see what we have to actually prove. We need to prove that, like before, when we said that we have S possibilities and N no possibilities, they are many. I mean, yes possibilities if they are not distinct, and N possibility, no possibilities when they are not distinct. But what we are trying to eventually prove is, even though they are all in a region R, the leaf node or the path that they take to form to come and find to find the distinct numbers for different permutations of x are different nodes. For example, let's take x1, x is equal to, let's say x is equal to 1 2 3, okay, and y will be equal to 2 1 3. So this one will take a different leaf node to arrive at the solution S, and this Y will take another different node L2 to find again yes. Correct? So when this happens, then for every permutation permutation for x, we have a different path. So how do we prove? This is our next topic. Next, so we have a different set of proofs. Like we saw, we tried to prove all the points stay in the same region, correct? And now we are going to take an instance x which says x1, x2, go on till xn, and y we say y1, y2, go on till yn. Okay, and now we try to say that this x and y are a straight line. Okay, and we have another point z, and we are trying to prove, now we are going to take z is equal to z1, z2, zn, which is equal to zi again will be lambda xi plus 1 minus lambda x yi. So therefore what happens is we are trying to, it's similar to ax plus by, which is a line equation, correct? So now what we do is, and we see that we take this lambda as 0 to 1, okay, 0 to 1. Therefore now when we consider, okay, when we consider only less than as our comparison, what happens? We'll be seeing in the next slide. So now what we are going to do is, we are going to find, now what happens is xi is smaller than xj, any two numbers, that is in case xi is smaller than xj and yi is smaller than yj. Therefore what happens is zi will become will be less than zc, correct? Are we together here? Yeah, so therefore it proves here that even z belongs to region R. Now same case we are going to have for xi lesser than xj and yi more than yj, meaning we know that these are two x and y are, y is a permutation of x. Now let's take x for example, let's take 1 4 7, okay, and y will be a permutation of this, which is 7, 4, 1. So here if you see xi and xj are lesser than each other, but yi is greater than yj. So what we are going to prove in this is, eventually, even if this is the case, still the elements are distinct. So therefore what happens is, because the elements are distinct, we will finally arrive at different nodes, which will be, this will, for example, L1, and this will be L2, and for a no quality we will go to another node for a no answer. Now, like we said, let's take xi lesser than xj and yi greater than yj. So we've proved that x and y are a straight line. We saw that, and we tried to prove there is a point set on the line, correct? So, and all these three will go to the same leaf node L. So now let's see for this case, but this one was for a less than case. Now for this case we are going to see now. Let's take a function f of w, which is wi minus wj. So now we know that f of x now is lesser than 0, f of y is more than 0. And when we think that it's a straight line and you have zi minus zj as x and y on the line, then we know that it has to pass through 0. So at some point of time, zi minus zj becomes 0 by mean value theorem. Correct? So therefore zi is equal to zj, which gives us a no answer. Correct? Which gives us a no answer, meaning therefore when we see no is a contradictory answer. Correct? So we have a no and two yeses, so they cannot be on the same L, even though they are on the same region RL and belong to a point P. They are not like X, Y, and Z, but X forms a different leaf node, Y forms a different leaf node, and Z forms a different leaf node. 1, 2, and 3. So this is a yes, this is a no, and this is a yes. So this proves us that x of n consists of distant elements, y of n be a non-trivial permutation of x, like we saw, then x and y must be distinct as leaves. So we find out that from our proofs that we have done, we have understood that they all end up, for different non-trivial permutation of x, they all end up at different leaves. So the number of s leaves therefore is equal to n factorial. That is, t of n becomes omega of n log n. So that is our proof, guys. So therefore we are trying to prove here that even though the answer is yes or a no, where only the possibility is a yes or a no, but we find out that we have a large set of elements also, different permutations of that elements. For example, you have an element 1 to 10 and the different permutations. Still, the time you sort and find out the yes value, you are going to land at different points, different leaf points at a decision tree. So that is our proof. Thank you.